Geri değişti. Ondan sonra nereye gitmeliydi?
Okay, good.
Farkları öğretmek için Reymen nasıl?
Okay. So, thank you very much for the introduction. I actually don't really identify as a computer architect, engineer, but I guess for here, that'll do. So, yes, so I'm really happy to present at this really beautiful workshop. Thank you so much for inviting me. And I'm going to talk about our Bayesian work, which I realize might not be the work those of you who know my work actually know the best. And I also want to clarify immediately that I work at the University of Paris-Saclay, but everything I'm going to present is joint work with the groups of Marc Bocquet and Jean-Michel Portal at Aix-Marseille Université, and especially the group of Elisa Vianello at Leti in Grenoble. But let's start immediately. So computing with physics, usually, which, I mean, we've been doing that for years, we try to use deterministic processes that are very interesting and that actually can provide directly computing. The reality is that many physical systems, and especially nano devices, one I'm working on, in particular memory store, so all my talk I'll be talking about memory store like this, have deeply non-deterministic behaviors. That's been a big problem to solve in recent years. And so with this talk, I want to make the point that actually this type of non-deterministic behavior, if you understand them, they can actually be very powerful to implement other type of computing, and in particular, Bayesian computing. So that's how I'm going to organize my talk. So first, I'm going to present what we traditionally do, which is to fight the randomness of nano devices, in particular, memory stores. And then I'm going to show what we've done in recent years, which is to actually more embrace the randomness of memory store, to do a particular concept, which is a Bayesian neural network, which has some really nice features, and even sometimes even exploit the randomness of nano devices as the source of computation itself. And we have done some kind of learning like this, using an approach that looks like Metropolis, Hastings, Markov chain, Monte Carlo. But let's start immediately by some context. So in my lab, we've been working a lot on these memory stores that have been mentioned before in other talks. These are nano devices. So the one we're using are hafnium oxide, and now they can be integrated on top of CMOS process. This is a cut electron microscopy of the process we are using. So you have the transistors that are here. Then you have metallic wires, and on top you have your memory stores. So these memory stores are nano devices. So it's really a sandwich of a resistive switching material between two electrodes. What we use is non-stoichiometric hafnium oxide. It means that this material intentionally has some defects. It has a lot of oxygen vacancies. And in fact, what happens is that when you apply a strong voltage, like a few volts, you can actually move these oxygen vacancies and create some filaments of oxygen vacancies that connect the top and the bottom electrodes. And these vacancies actually conduct electricity. So when you have created these filaments, your device ends up low electrical resistance. And when you apply a strong negative voltage, you can actually move your vacancies the other way and dissolve your filaments and reprogram your device to high resistance. And atoms do not move by themselves, naturally. So that means that when you don't apply a high voltage, actually the resistance of your device is not changing. You have a device that is actually a memory, and the memory state is the electrical resistance of the device. High voltages program the memory, and low voltages allow reading the memory resistance. And it's nano device. It's very small, it's very fast, it's non-volatile, and it's really on top of the CMOS, fully integrated. And the reason we're particularly excited about them is that in a way, these devices resemble artificial synapses. And to understand this, you see the magic kind of happens when you connect them in an array. So you see here, if I have an array of memory stores, I can have horizontal wires where I apply voltages. Then the current that will go through each memory store is going to be, due to Ohm's law, the product of this voltage by the inverse of the resistance of the memory store, which is called the conductance. And then all these currents, they go to this vertical wire. And so the current that goes here is a weighted sum of all these voltages by the conductance of the memory stores. If you consider the conductance of the memory store as the synaptic weight, actually you see that by just making an array of memory store, it will naturally implement the equation of a neural network. And so these analog electronics, and it happens directly within the memory. So it totally avoids the von Neumann bottleneck that Peter has mentioned before. So it's a way of implementing the equation of a neural network that should be extremely energy efficient. And it has motivated tons of research on these devices. And it's been quite difficult at the beginning, but now we've made a lot of progress. And now many groups, including us, can actually do that in practice in real systems. So this is our implementation. So you can see, so this is actually fabricated by Leti. And so you have an array of memory stores and fully integrated on top of CMOS. And around the array, you have CMOS circuitry that can actually allow to do all the tricks that are needed to make it work and to be actually able to program and read the memory stores. Because, yeah, spoiler, but the reality is a bit complicated, more complicated than this cartoon. You need to add a lot of stuff to make it work. And here is an example of something we did experimentally. So we actually programmed a full neural network using this technology. So this is a simple two-layer neural network. We need one array for each layer. The input is a heartbeat, and the output is if the heartbeat is healthy, or if it has a disease, a type of arrhythmia, and what type of arrhythmia. And we managed to program our memory stores to make it work. So this is the result. Accuracy, so when we present thousands of heartbeats, what is the accuracy in recognizing them? As a function of how many different levels we programmed our memory stores to. That means how many different synaptic weights are possible. And you see that the more levels we have, higher the accuracy. Maximum is around 9 and is very close to what is possible with software, which is our baseline. So it looks amazing, but it's very difficult to do. And one of the main reasons is that memory stores are very, very imperfect. When you create these filaments, and these filaments have really atomic size. That means that each time you program a memory store, you actually get a result that is quite different. So actually, to model memory store, we very much use the language of probability. This is the probability. So here is actually the distributions of state of the memory stores when you program them for 8 different programming currents. And so ideally, you would want that when you use one current, you get a very precise value of the conductance. But what you actually get is a distribution. You can even see that the distribution, unfortunately, they overlap. And when you go to low constant, they actually overlap quite a bit. So that's way too imperfect to implement our neural network. We actually need to fight this behavior. And what we do is actually quite simple. Actually, everybody does that. It's program and verify because this is probabilistic device. Basically, if you program it and you don't get what you want, you try again until you actually get the resistance you wanted. And then when you do that, you are able to really tighten the distributions. And you can see now that my distributions of conductance are actually separate from each other. So you get way better states. So that's how we got this result. So we were initially happy, and then we realized something. So measurement I just showed was right after programming. If you redo the experiment a bit later, you realize that the accuracy on recognizing arrhythmia actually drops. 2 months later, it has dropped from 95%, more something like 87%. And the problem is that, in fact, these filaments are not perfectly stable. Some of these oxygen vacancies, there are different types. Some of them are actually quite stable, but some of them are actually quite mobile. And so if you are unlucky and you have programmed your memory store with a mobile vacancies, well, the state is not perfectly stable. That's what what you see here. Here's the distribution right after programming. 1 hour later, they've actually broadened. So we need to fight harder. And so what we realized is that some memory stores are actually stable and some memory stores are actually unstable. So we made our program and verify more complex. Now we program the memory store, we wait 1 second. If it has not changed, we consider it stable, we are good. But if it has changed, we actually try again until we have managed to program the memory store in a stable state. When we do that, we finally are able to program our memory store neural network. It has stable accuracy. 2 months later, we still have our 95%. So it is actually possible to fight memory store randomness. And actually right now, industry is working massively on making more sophisticated version of this type of techniques. to fight this. In a way, I mean, back to what has been said before, it didn't feel that natural. It really feels like we are going against the device physics of this memory source by really forcing them to tighten this distribution. And when we are doing that, we are really not doing physics. We are doing statistics. So that's why I'm going to talk about new work that takes this problem extremely differently. And our insight is actually to focus on Bayesian models of machine learning. So Bayesian models are a type of model where everything is supposed to be a random variable. And these random variables, they tell us about the knowledge or the certainty about things. For example, if you take a conventional neural network, each synapse, each neuron, they have a specific real value. If you take the Bayesian version of a neural network, it's different. Synapses are actually random variables that follow a probability distribution that tells us about the certainty about the synapse. A synapse has a very large standard deviation. It means we don't really know what the value of the synapse is. If it has a very low standard deviation, it means we have a very precise idea about what the value of the synapse should be. And then due to that, the neurons actually also follow probability distribution. And that will tell us really the knowledge about things. And the insight we had is that we have this class of neural networks that are very powerful. We are going to see why. That are very hard to compute also because everything is probability distribution. And we have these devices that actually very naturally act as random variables and follow probability distribution. We felt there has to be a way to really use the random character of memory stores to implement a Bayesian neural networks like that. And before explaining exactly how we did it, let me say a bit more about Bayesian neural networks. So Bayesian neural networks are quite different from traditional neural networks. Traditional neural networks, the ones are learned to really minimize the error on a training data set. Train it, reproduce a training data set no matter what. Bayesian neural networks, they are trained to do something more subtle. Weights are going to follow a probability distribution. This probability distribution should approximate really what is the conditional probability of the weight given the training data set. Like really identify what are likely reasonable weight values to explain what the training data set is. And kind of different hypotheses explaining the training data set. This seems something that should be very hard to identify. That here we can use the magic of Bayesian statistics, which tells us that due to Bayes' law, the probability of the weights knowing the data set is really the same thing as the probability that we would observe the data set given a certain value of the weight. And this one is actually a lot easier to estimate. There are multiple techniques for this because you kind of compare your data set with the weights and you identify how likely it would have been to obtain this in-training data set. So training Bayesian neural networks is actually something that is very feasible. And Bayesian models, they tend to really excel in situations where you have a lot of uncertainty, where you don't have that much data. So here is a kind of cartoon example, but a real example. So this is a neural network that has two inputs, 1 and 2. And so you have a training data set, which is the triangle and the circles. And the goal of the training is to identify when you have an input, if it's a triangle or a circle. If you try a conventional neural network, it will do something like this, like it will identify a boundary between the triangle and the circles. And you see, you have this triangle here. Find a way so that the triangle is actually red. So this is a training that has succeeded. Training accuracy is 100%, but the model it found is a bit unreasonable because it made this very strict boundary here, but honestly, it could also be here or here. You just don't have enough data for doing it. And what it found so that the triangle is red, something that honestly is very unlikely. That's really the situation. That means that when you actually use your model later with other data, well, it's going to be like, for example, if your data point here is going to tell you red 100%, but honestly, we can't know. And if you put the data here, the prediction of the model is just not reasonable. So this situation is called overfitting. By contrast, the Bayesian neural network really identified all possible models that are likely explanation for this. So you can see that on all these regions, it has these light colors, which means it doesn't really know. It's not a certain prediction at all. And for the red, it has actually understood that probably think it red is not the most reasonable explanation, more likely kind of an error in the data set. And it has avoided to do something like this that is very unlikely. And these are very strong consequences in practice that for example, so when you present, for example, when you train a conventional neural network, recognize images of cats and dogs, it will recognize cats and dogs. But if you present an image of a giraffe, it will tend to make a prediction. Well, this is a cat, and I'm quite certain about it. Yeah, that didn't sound reasonable. And on the other hand, the Bayesian version itself, when you present an image of something that is unknown, will be able to tell you, I don't know what this is. So we did that in practice. And so we use our memory store memory computing arrays. So what we did is that we actually took 50 different implementations of the same neural network, and we program each memory store the same way. But because memory store act as random variable, each of the memory store is actually going to have a different value. When you present an input, all the outputs are going to be different, and the distribution of the output is going to tell us about the certainty of the Bayesian neural network. But how do we program the memory stores? So here we have another problem, that when you train Bayesian neural network, so each synapse has a mean value and a standard deviation, but it's really due to the data. So the mean and the standard deviation can take any value. In a physical process, so the mean, because the random character comes from physics, mean value and standard deviation are actually connected. You have these two curves. One curve is when you don't do program and verify, like the natural behavior. This curve is when you do program and behavior. So you don't get the flexibility you need for doing the Bayesian neural network. But it can be fixed actually quite easily by using two memory stores to do one synapse. Because when you have two memory stores, you can kind of choose the standard deviation and mean independently. And so what we do is that we have two memory stores, and the actual weight is the difference between the two conductance. Then you can do a wide range of mean value and standard deviation. Not everything that is possible, that is quite broad. And then when we train the neural network, so training is done off chip on the computer, we use a standard technique in Bayesian neural network, which is to minimize the divergence between the neural network and the actual probability that we want of the weight given the training data set. And when we do that, we add an additional term, kind of force the mean value and standard deviation of the synapses to belong in this regime of what is actually possible. And when we do that, it actually worked well. So when we present an input, now we have different possibilities. And sometimes you present a heartbeat, and all neural network actually give the same answer. You know, it's a clear prediction, and the certainty is quite high. Sometimes what happens is that all neural networks, they all hesitate between the same type of arrhythmia. You know in that case that the input is probably something that is kind of unclear in between these two types of arrhythmia. It kind of looks like both. That's what we call aleatoric uncertainty. And sometimes you have the most interesting situation, like each neural network actually makes a different guess. And this type of situation, it's really the situations where you present an input that looks like nothing that was in the training data set. And so each neural network has made a different interpretation of what it could be. That's the clear sign. And so we did that experimentally, and we presented thousands of examples. And we looked at the statistics of what's coming up, particularly in looking at this uncertainty, which is really based on the dispersion of thank you, I like it better, on the dispersion of the output. And so you see that when the neural network makes a correct prediction, that it actually got the right answer, usually it's very certain of its choice. Just a few times, it actually was unsure. when the neural network made an error, I mean, didn't recognize the correct arrhythmia, it never was certain. Always it told you, I'm unsure. And when you actually intentionally present something that doesn't look like anything in the training data set, each time it has a very high uncertainty. That's really the giraffe cases that I mentioned before. That's very quite different from a traditional neural network, because traditional neural network, as I was telling with the giraffe, tends to have very high uncertainty when you present something that doesn't look like anything like the data set. And so that's very beneficial, actually, particularly for some safety critical applications, like medical applications. You really want to know the neural network is not sure of his choice. The thing that is also nice is that now the memory stores, they are not really supposed to represent a specific weight value. It's supposed to represent a specific probability distribution. So it doesn't matter if they are not stable, as long as they represent the same probability distribution. And so you see that even without doing program and verify, we have a performance that is stable over weeks. We're not able to test longer. And also, so we made this experiment on 50 implementations of the neural network. That's because we wanted a lot of statistics. But actually, 50 is not needed. We are able to get the same performance if we use only 10 implementations of the neural network. Okay, so I'm going to go on the last project, but 5 minutes should be okay, which is an even deeper way of using the imperfections of the neural networks. Because this neural network was actually pre-programmed. We trained on the computer. But if you want to do training with the memory stores, it's actually very hard, because you need to change your parameter value very progressively, as Florian mentioned before. But when it comes to training Bayesian models, there's another way of training, which is to use Metropolis Hastings Markov chain Monte Carlo. It's a way of training where you actually create a Markov chain of models, and each new model is generated by sampling randomly based on the value of the previous model. And we know the memory store, when we program them, actually they follow a random distribution naturally. So it seems that just programming the memory store to naturally implement the sampling step of this Markov chain training technique. And that's actually very easy to do in hardware. If you imagine an implementation where you have an array of memory store, and for example, the different parameters on different columns and the different rows of the different versions of the model in the Markov chain, actually, you can just take the current that flow in the memory store, re-inject it to the next memory store, and it will naturally reprogram the next memory store following a sampling step as is needed in the Monte Carlo technique. And we actually did it in practice. So in that particular case, we actually don't have a full system. We just use a big memory store array, and the rest of the system is emulated on a computer. And we train like this, a very simple neural network, recognize cancerous images of mammographies. It actually worked really well. Actually, that's probably the only time in my career that it actually worked better than the simulation told us it was going to work. That's because all your problems, you put them in this probability distribution, and then they kind of disappear. So here, so in that particular, we have 256 versions of the model in the Markov chain. 256, once again, was not really needed. It's a tiny neural network. It has only 16 parameters. And so you see, you get all these versions of the neural network, and the synapses have each time different values. So the synapses really follow probability distribution. Then you get all of these models. Each of them can recognize cancer, and they all have different accuracy. Some are much higher than others. If you pull all of them together, you are able to recognize with 98% accuracy, which is as well as the software could do. This process that is very energy efficient. And is really learning due to the imperfection of the memory stores. So I conclude my talk. So yeah, I think I made my point that incorporating non-deterministic properties as Bayesian can have some really powerful, and there are declination of this concept for inference and learning. It's really useful for high uncertainty situations. And the idea is not necessarily to train ChatGPT using this type of things. One highlight, I insisted on this because I think it's very physics-driven technique. It's not the only way that nanoelectronics can help Bayesian concepts. So in particular, if you look at our work and you find our Bayesian machine, that's actually a quite different way of approaching Bayesian statistics that is not physics driven at all. But I added that because yesterday some people asked me questions about it. So I wanted to make clear Bayesian machine is something that is very different than this. So I want to acknowledge all our collaborators. I mean, this type of work requires a lot of collaboration. I thank you for your attention.
Thank you very much. So, question, we have 5 minutes for questions.
So great talk, Damien. So with this Monte Carlo-based learning, do you in every step have to calculate the likelihood of all the training samples given? And isn't that quite a lot of effort? Or can this be optimated by only taking batches? I don't know.
You absolutely need to, when you do a sampling, you need to either accept or reject your sample. And depending on the model, it can be quite complicated or not. So for example, in the cancer dataset, you actually have to go over the whole dataset. Other tasks, like in our paper, we also have a reinforcement learning task, which is this CART-POL thing. And in that case, calculating the acceptance is actually extremely easy, very low computational. It really depends on the model. But that overall, it's not something that is adapted for a very large dataset.
Me over there.
So probably a stupid question. So can you narrow down the distribution by coarse graining the members here, like averaging over blocks of members?
Yes. And people actually do that for analog computing. For example, IBM has multiple papers. They typically use 4 memory stores for each synapse for this reason. Yes, very good idea.
Very good talk. One thing that I didn't particularly understand. So you have 50 realizations of your network, and each one of them has particular values for the conductances. So it wasn't clear to me what you meant by one of them saying, I don't know what the answer is.
So each of these arrays has, like, for example, if you have 10 possibilities for the output, so either healthy heartbeat or 9 different type of arrhythmia, sometimes it happens. So this case would be that each of them gave a very clear answer that's arrhythmia type 1. But it can also happen that each array itself was hesitating between arrhythmia type 1 or 2. They give kind of equal output on arrhythmia type 1 or 2. That is different from this situation where each array was quite sure of something different. So, and then we have very clear equations that comes from Bayesian field, kind of put a number in terms of uncertainty based on the statistics of the output.
I have a follow-up question to that one, which is, do you know the memory density that you can get with these devices, especially if you're using, when people are using many of them?
You mean in terms of literally area?
Literally area, how much memory you can fit, and compared to, like, I don't know,
So
SRAM.
resistive RAM scales perfectly because the filaments are very tiny. So actually, to some extent, it hardly doesn't matter the area of the cell. The one thing that doesn't scale that well is that typically you need to associate each of them with one transistor. And this transistor needs to be able to pass enough current to program the memory store. So the cell of, or the area of the cell is really the area of the transistor, which literally means the same thing at the current you need to actually program. So it depends, for example, so it's actually a complicated question because it depends also on the reliability you want, because the higher current you use, the more reliable your device is. But typically, current industrial process, and I'm really giving an approximate answer because this is NDA topic, are 10 times more, I mean, for very modern CMOS processes, it would be 10 times smaller than SRAM. And it's probably going to become even smaller. For an older process like this, the difference is smaller.
If you scale it down, those probability distributions also get impacted.
Yes. So then there is a lot of engineering beyond this. And it's not only about the memory source. The CMOS, because, for example, if you make the smallest transistor possible, the transistors are going to have variability themselves. So the distributions you see are also going to have a part that is due to the transistors. So there's a lot of engineering behind all this.
Yeah, but the transistors would be mostly used as a switch in that case, right? So
So,
what impact does?
so this very particular technology, at least in the way we are using it, they are also used as a current limiter during the set operation. This actually determines the final state of the memory store. So in the way we are using them, they're actually a bit more than a switch, but there are techniques to fight this as well, like to rely a bit more on the periphery, to use them more like a switch. And in that case, indeed, they will not matter that much.
Sorry to say quickly, maybe an immediate follow-up, because there's been people waiting in the back. Go for it.
I think one of the questions I was thinking about is, in some ways, you can kind of characterize the device-to-device variation you'll see across different chips. When you're training it, if you kind of utilize that data, would that help your performance even more? Have you tried that?
That's a very, very interesting question. In the very particular way we're using it, it doesn't matter that much, the difference between device to device and cycle to cycle. But depending, for example, if you reprogram arrays, or so if you read noise, which is something you can use for that, that's going to be very, very different. And so this difference Bayesian scheme, some of them device to device or circle to circle are quite different. In the case of our device, in the regime we are using him, both of them are actually quite equivalent. We hardly have a difference between cycle to cycle and device to device. That's not the case of all devices, and that can have very, very big consequences on this type of ideas. For example, for phase change, it's very different.
Oh, there's so many hands. I think we're going to have to restrict ourselves to 2 more questions. So I don't know. You want to self-organize over there? You've been waiting.
So just on the energetics, I think you quoted the 6 microjoule number. Could you compare for that exact same example what the traditional energy costs would look like? Just what is the order of magnitude gain?
So I have to just take this number with a grain of salt. So because this system is not fully fabricated, so this 6 microjoule, my student actually designed the system, and this is based on simulation of the system. It's not a 7 microjoules that has been measured. So in that particular case, so we have 7 microjoule. We are doing the same algorithm on a Xeon CPU, be 600 millijoule. So probably, I mean, so that's 2021 paper. And now when we do this type of benchmark, we actually use computers that are a bit more energy efficient. I think this could probably be reduced quite a lot, to be totally honest with you. But yeah, it's still a very, very big difference.
The next half of the room, I think I saw a hand at the hero.
So I thought it was really interesting from a philosophical perspective that when you get unknown data, all the different chips are very sharp, but they have different opinions. You could imagine that for humans, asking experts, if you're seeing something that has never happened, they will just give you.
Yeah, I should correct you immediately. So I made a poor judgment call to simplify my slide. But what really happens in this situation is that typically each of them hesitates. They hesitate between different things.
Okay, so they all will hesitate. Then what is the difference between this and the previous slide where they all go?
So what happened in that case, they hesitate between the same things. All of them hesitate between 1 and 2. And in a situation of epistemic uncertainty, what typically happens is that they all hesitate. This one hesitates between type 1 and 2. This one between times 3 and 5. This one hesitates between 5 and 7. So I simplify my slide so to make it more readable, but that's very poor judgment call. I will change it.
That makes more sense.
Thank you for this question.
Well, I think we have to call it there. Those who have extra questions, of course, please find them in the breaks. And with that, let's thank you again and